Here is the first kind of new topic in grade 12 physics, relative motion. So relative motion is a topic that really doesn't seem to fit very well in the grand scheme of grade 12 physics. It's like this odd uncle that's been thrown into your family gathering. You don't know where he came from. You don't know where he's going after he leaves. But he's there. So we're going to do relative motion. It connects to Einstein's theory of relativity, but we're not even going to go that far. We're just going to talk about relative motion on its own, not connected to any of that stuff. So let me draw you a picture of what's going on here, and then we'll solve some problems. So let's say you are an incredibly rich old man or rich old woman, and something that you have really wanted to do all your life is what you've admired in the movies, running along the top of a train. You know, those chase scenes where you have one person who has stolen something and starts running across the top of the train, and there's somebody chasing after them. That's what we're talking about. So here's our train. Let's make it a red train. Here's our train. Wheels. Second car. We don't really need both cars though, because really all that's happening is you are going to be running across this train. Okay, so here's you running across this train. There you go. But because you don't really want to injure yourself, you have decided to run just on the top of a train for practice. So this train is not moving. But let's say that you can run at 3 meters per second. So here's your velocity. 3 meters per second. So to you, from your perspective, you seem to be moving at 3 meters per second forward, and the train is standing still. Okay? That's a normal situation, right? But you're extremely rich, and so why would you use your own legs to run when you can have somebody move the train under you instead? So we're going to get rid of your running, and then you've hired a train. No, you've hired a crane. Here's our crane. And this crane is connected to a harness, and it's lifting you up. Okay, so now you're going to be lifted up a little bit, and so you're just barely touching the train, and now you've got somebody in a giant bulldozer is going to push this train. My drawings are amazing, aren't they? I don't even know where I'm going with this. Here's the bulldozer. There you go. It's going to push the train at 3 meters per second. Okay, so now you're hovering in the air, just barely able to touch that train, and now the train is moving this way at 3 meters per second. Okay, now what's the difference from your perspective in these two situations, other than having to wear a really uncomfortable harness? Nothing. There's no difference between these situations, right? In one case, you were moving along the train, you were moving across the top of the train at 3 meters per second, right? And in the second case, the train was moving under you the other direction at 3 meters per second. It was moving this way at 3 meters per second. But those are exactly the same thing. 1 second later, you, instead of being over here on the train, you are over this part of the train right over here, right? Whether you are moving east on that train or the train is moving west underneath you, those are exactly the same thing. That's called relative motion, because from your frame of reference, it doesn't matter whether you are moving forward or the train is moving backward, it results in the same thing. This is a one-dimensional version. You are moving forward, the train is moving backward, we're only dealing with east-west. There are also two-dimensional versions where maybe there's east-west motion and there's north-south motion, or maybe there's an angle in the middle there. So we're going to solve some problems having to do with relative motion. A person is walking to the right in a moving train. Trains are really popular for relative motion problems. I don't know why. Maybe because they always move in a straight line and they're really long, so it's useful. The person is moving at a velocity of 3 meters per second to the right in the train, but the train is also moving to the right at 20 meters per second relative to the ground. How might a cat on the ground view the velocity of the person in the train? Here's the train car. Here's the person in the train car. And the person in the train car is moving at 3 meters per second to the right. And according to the person, that's how fast they're moving, because their frame of reference is the train. And they see the walls of the train, and they are moving 3 meters per second to the right in the train. And so what they see is the train surroundings moving past them, backwards past them at 3 meters per second. Okay, so that's how they know they're going 3 meters per second. But if they would look out the window, they would see that the train is also moving at 20 meters per second to the right. Okay, and so now the question is, this cat that's sitting on the ground over here, oh boy, why am I trying to draw a cat? Here's a, there, it's perfect. This cat sitting on the ground here, how fast is the person going past the cat? So if the train was standing still, the person would be passing the cat at 3 meters per second. But the train's not standing still. It's also going at 20 meters per second. And so the velocity of the person relative to the cat, here's how we write this. Velocity of the person relative to the cat, VPC, is equal to the velocity of the person relative to the train plus the velocity of the train relative to the cat. Okay, there's a kind of chain going on here, and let me show you what that is. Let's just change colors real quick. So we're looking for the person relative to the cat. We want the person's velocity relative to the cat. And so our chain of velocities in this formula starts like this. Starts with the subject. Okay, we're looking for the person's velocity. So the person is the subject here. And the reference is the train. So the person sees themselves going 3 meters per second in the train. Then we don't really want the train as our main reference. We want the cat as our reference. And so we take the train as a subject and the cat as the reference. And so now what happens is this formula that we've created takes the person and gives us their velocity according to the cat. So the very first thing is the subject, and the very last thing in our formula is the reference. Now, some people find this formula thing useful because they really love formulas. That's fine with me. But other people just want to logic this through. Okay, and that's also totally fine. In order to solve this question, I do not need you to write down this whole formula over here. That doesn't need to happen. I just need you to show what you did. Okay, and so if you just wanted to go, the person's velocity is 3 meters per second, or the velocity of the person relative to the cat equals 3 meters per second plus 20 meters per second equals 23 meters per second to the right. That is also perfectly fine. In essence, what you have done is the formula, but you don't need to be that formal about it. I'm fine with that. Second one, see if you can just think this through before I write anything down, or pause it when I'm done reading. You're going up an escalator the wrong way. Of course you are. To someone standing on the ground, you look like you're going up 1 meter per second. Up? What did I say? You're going 1 meter per second up. But you're moving against an escalator going 2 meters per second down. How fast are you moving relative to the escalator? Okay, so what the question is asking here is, if you are just looking at the escalator and nothing else, how fast are you moving relative to the escalator? Or what does the escalator see you doing? Okay, that also works. Think it through, see what you can do. All right, here we go. Hopefully you paused in there and actually tried to think it through. So you're going up an escalator the wrong way. We're actually just going to call this direction up and this direction down, or up the escalator and down the escalator. Okay, so you are standing on here. Whoa. That doesn't seem anatomically quite right, but you know, whatever. Maybe you're doing lunges up the escalator. So, to someone standing on the ground, an observer over here, it looks like you are going 1 meter per second up. Okay? But you're moving against an escalator that's going 2 meters per second down. It's going past you at 2 meters per second. How fast are you going relative to the escalator? Okay, so if your total velocity is 1 meter per second, this person sees you going this way at 1 meter per second, but the escalator is passing beneath you at 2 meters per second. How fast are you moving relative to, the escalator is moving 2 meters per second down relative to the person on the ground as well, relative to the observer. So then how fast are you going? You are going, relative to the escalator, you're going 3 meters per second up the escalator, right? Because it's going past you 2 meters per second, and you are going upwards 1 meters per second. So both of those things together would give you 3. So using our formula, here's how that works. We wanted the velocity of the person relative to the escalator. So that's equal to the velocity of the person relative to the observer. And the velocity of the observer relative to the escalator. Okay, we've got to make sure that the chain is working as it should. The person to the observer, observer to the escalator. Okay, so this gives us 1 meter per second. That's the velocity of the person relative to the observer. The velocity of the observer relative to the escalator. So the escalator is moving past the observer at 2 meters per second that way, which means the observer seems to be passing the escalator going 2 meters per second the other direction. And so this is 2 meters per second, also up the escalator, which gives us a final answer of 3 meters per second up the escalator. Try the practice. That's the best way of figuring this out.